Alright guys, so I'm trying this problem. Construct binary tree from preorder and inorder traversal. Given two integers, preorder integer arrays, preorder and inorder, where preorder is the preorder traversal and inorder is the inorder traversal, construct and return the binary tree. So this is the tree. You can see the preorder traversal is okay. What is preorder? Is I think it's root and left and then right, and inorder is left, right. So if you look at the pre-order of this, it would be 3, 9, 20, sorry, 3, 9, and then here also, yeah, so 20, 15, 7, and in order would be left to right, 9, 3, 15, 27. And then we build out the, what do we return? We return a tree node, so we return 2 to the tree, fair enough. If pre-order is -1, in order is -1, then the tree is -1. Let's see some guarantees. Pre-order length is 3000, so in-order length is pre-order length. Number of values rise to -3000. All unique values. Each, so I mean, this like basically everything is legal. There's no illegal input is not given. Length is also 1 year, so nothing, no illegal inputs. Pre-order is guaranteed to be the pre-order traversal of the tree. In-order is guaranteed to be the in-order traversal of the tree. Okay. Now let's try and build a solution. Let's think more with this example itself. What is it that we can get from this? One thing that we can get is the root of the tree is the first guy on the yeah, so that is the facts, right? So first element in preorder is the root. That is quite certain. What else can we figure out? So we figure out the first element. This has to be root. Now, where does this element exist in order? Okay, here. So all the elements to the left of this element is in the left subtree. All the elements are in to the right are in the right subtree. So that is clear. Now, can I say that this is the left child, this is the right child? Not clearly. Okay. So what else can we figure out? So once I get the root, I have to go to the left subtree, which would be on the right, on the left of this. And in the pre-order root, after that there is left. And then there is right. So from here we can see 9 and 9. As soon as I find an element, because they are unique, that is an important aspect that we can rely upon. As soon as I find an element which is to the right of 3, that is the element that is in the right subtree. And it's not just the right subtree, it is the because it's pre-order, it is the right child of 3, right? And in terms of the left child of 3, for the left child of 3, I see 9. Yeah, so I think it's quite obvious that in the pre-order there is root left, right? So it's not necessary that the cycle element is the left subtree, but it's the it's the right child. Uh, Left child of root if it is on the left side of root in order, right? And right child of root if it is on the right side of root in order. So you know this about the second element now. Okay. Now what about the third element? Because but we get to this root, now we have to go to its left and right. Uh, but as soon as you hit 20, you know that 20 is on the right side of 3, so it's the right subtree. So that's how you go 20 is the right child. Okay, so what I want to do is I want to just look at these arrays and not look at this tree, which is giving hints to me. So these are the only trees, right? And now let me try and build a tree on my own from this. So what do I get from this? I know whatever is the first element in preorder is the root. So 3 is the root. I find 3 here. So I add these boundaries, right? This is the left child, this is the right child. Fair enough. Now I go to 9. I see 9 in the left, so it has to be the left child. Okay. Then I go to 20. 20 is in the right. So I know that 20 is in the right. So 20 is this. Okay. So I go to this 20. I break these barriers as well. This is the 20's left child. This is pretty easy now. So 15 is 20's left child. 15. My bad. Sorry. Yeah, that's correct. And 7 is its right child. At least this is one solution. Now let's look at the tree that, yeah, it's exactly the same. Yeah, this doesn't help. Um, so what would be the approach? So the approach is sort of you get the root. This is the root that you're looking at, and then you go to the next guy. If the next guy is on the left of 3, then it's the left child. Let's take some slanting trees just to understand the example. So let's say there is a tree 1, 2, 3, like this, right? So what would be its preorder? Preorder you go 1, then 2, and then 3, and then 4. This is how the preorder would actually look like. And in order, okay, in order would look like left child, left, root, right. So left is nothing, it's the root, and right is, yeah, they're kind of the same actually. Am I correct? So 1, 0, 1, and then it's right child, nothing, 2, then nothing, 3, and then 4. Yeah. Okay, so now if I am not given this, I will go with the preorder. I'll know 1, and I know that there's nothing on the left of it. So when I go to 2, I know that 2 will be coming to the right, and I look at 2. Yeah, I can sort of draw the boundaries. Like when I went to, yeah, I can sort of draw the boundary saying that, hey, 2's left is only till now. Basically, yeah, this one was the last boundary. So after 2, I go to 3. 3 is to the right of 2. So this. Then we go 4. 4 is to the right of 3. Yeah, okay. So this is bullshit. Now let's do this. 1, 2, 3, 4. Or how about this guy? So what does pre-order look like? Pre-order is 1, 2, 3, 4. In order is, yeah, and this is a good one. So in order is left, root, right. So left, root, yeah, and basically it's this. So we got, when we walk through the pre-order, we get 1. Then we go 2, 2 is to the left of 1, so we go 2. Now we consider root as, so now we consider this and this, these two, right? These are the two that we are considering. And we get 3. So 3, first we consider with 1. 3 is to the left of 1, which is good. 2, but is it left of 2 or right of 2? It is to the left of 2. So it goes here. Now we're considering this and this. And we go to 4. Yeah, I think that's my problem. Like, uh, because when you see 4, whose left or right are you checking here? Ones, twos, or threes? Maybe start with this, right? Okay. Some random tree now I want to try some random tree. Or can I build up upon some solution? So the algorithm that I'm seeing is this: I walk through the pre-order array. For every element, I find its position in the in-order array, first guy, and then for based on that, I get the hint of how many elements are in the left subtree, how many is in the right subtree of that. For example, let's do a walkthrough of this guy again. I knew 3, so I knew 3. Now I'm only considering 3, okay? And I go to 9. This is my 9. Now, so when I made 3, this is my node. Let's say there is a variable called node which is set here, right? And when you add 3, you know that 3 is in the left side of 3. So we go 9. Now my node is 9. And maybe I keep track of the parent. Maybe, yeah. So that is fine. I keep track of the parent. So when I'm done with this, I can go to back to the parent. Is there anything to the left of 9? No. Is there anything to the right of 9? I know, but between 9 and 3, there is nothing. So when you go 20, 20 is to the right of 9, but also to the right of 3. I think you have to move back to the parent directly when there is no left or right, and you can figure out when there is no left or right for a guy based on this pattern, right? Yeah, so you go to parent index and you get the nodes index, and you compare the nodes index with the parent index. Yeah, I think I can figure it out. So let's walk it again with the more towards like how we would code. Um, so I'll have a variable called no parent and node, right? And basically I'll initialize, let's do this. I'll initialize my node to this 3 guy, right? Node would be pointing to 3. And when I find this 3, no 3, I'll search for this 3 in the array. I'll get it here. I'll save its index. That's the only thing I need. I'll save the index and then I move on. 9. And I find that 9 is on the right side. So I add the left guy and I keep track of the parent. Now I check whether this 9 has uh, a left child and a right child or not. Right? And let you check based on the distance from left, like 0th index till 9, there is nothing. And distance between the parent and this guy, and there is nothing. So that's why 9 is done. So you come back to 3. And now you move to 20, and you check 20 to the is right or 3. You find its index. And you can see there is something to the right, something to the left. So you remain at 20. And from 20, you move to 15. 15 is the left child. And from 15, you see, can I go to the right? Can I go to the left? And you can or you can't, right? And after 15, you go to 7, which is to the right of 20. Yeah, I'm not still not able to make a foolproof solution, but let's try and start coding it up to see what we're thinking of. Okay, so we are walking. First of all, uh, tree node root equals to a new tree node preorder of 0. Okay, this is done. Now I walk in my approach. I'm walking to the preorder array. So int I equals to 1, I is less than preorder length I plus plus, and at the end I will be returning root, and I could probably do, let's say if I need parent, so parent is null and current is root. Yeah, this is the situation. So what I do is once I find, yeah, so I found my guy. Once I find this guy, I also want to find its position in order, right? So for we are searching in order from 0 to Inorder length minus 1, and you are searching for PR of 0, right? This is what we are searching for. Let's write this utility function int search array int l int r int target. We expect it to find, but if for whatever reason it doesn't find, minus 1. So we search the index. So we know where root is present in the uh, Inorder array. Okay. And now we go through the preorder. What do we do? Let's also just define left and right, yeah, for our sake. Left equals to 0, right equals to, just call it L and R maybe. Yeah, L and R is -1. So here we can call L and R instead. So L, and here we call R, right? Now, the thing that we want to check now is when you move to the next guy, you want to check if this next guy, we search for it. Okay, let's call it int, I don't know what to call it. Make it this left index. So we search this array from L till this index position, actually index -1 rather. And we are searching for what exactly? We are searching for preorder of I, right? If we find it, that's good. If it's not -1, then you do current.left equals to new free node preorder of I. And now what else? Now you call parent equals to current, and current equals to, how do you keep going up? That might be another problem. You have to do some sort of a recursion here. Because if you keep going down, 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 how do you keep coming back up, up, up? Uh, Interesting. So I think what I need is to somehow build both current.left and current.right. Okay, let's try recursion and see if it works. So ultimately what I'm doing is dot left equals to, let's call it build tree. You give it your preorder, you give it your inorder. At preorder, what index am I at currently? I'm at index 1. In inorder, what I will give is the range, right? I can only go from L to index -1. From this, I have to build my current.left, and current.right is again, you build your tree. Now this is the bit that which index you check. Do you check index 1 again, or perhaps not, right? Hmm. So you know what? this guy would break out because preorder is left root and then left and then right. So we go here. So this 3 9. Then you go 20, which is on the right side. How do you know how many elements? So this is simple enough, no? You got this index. So number of elements here, those many elements you move to the right. Yeah, okay, so go till here, 1, and then here you build so what do we get? So number of elements in the left subtree is how much? That would be index, whatever I find, minus 0. So for example, in this case, index is 1, so number of elements in the left subtree is 1. So yeah, index minus 0, which is we can call index minus L. These many sub elements are in the left subtree, and next guy is the right. So plus 1 is the root at, and plus 2 is where the our position is, right? So you go index plus 1. This is in the in order. Yeah, this is in the pre-order. So index plus 1 till R. Okay. Let's do this. This is the pre-order index that I'm checking. In order, this is left and right. Okay. Now what am I doing? I will be doing the same thing actually, which is this much. So I find this in what? Okay, so pre-order of p index. That's some difference. So I find this element, and before all of this, there's another thing to do, which is if the index is less than 0, or then we don't have an option to but return null. Now we find this guy, and the question is, will we find it? Right? That's one question, and the answer is yes. You will always find it. Okay, so we find it. We get the index, and then we build its left and right, and we return current. Oh, this seems to be becoming pretty easy when you do recursion. Now my question is, because this is repeating, can I move even the first guy here? Why not? So you call build tree pre-order. Okay, so then I'll have to call something like build tree pre-order, start with index 0. In order, search for it from 0 till in order dot length minus 1, and you just return this guy right away. In that case, you don't need all of this. There is no parent, root, nothing. Even this is not needed. Okay, there is a. I think I did a bit too much. You have to create a new node though, right? And so I'll just call it current then. Okay, let's try to do a dry run for this guy. 3/9/2015 7. Okay, so what will happen here? We're calling this build tree, which is fine. We're only interested now in looking at this code. So index is 0. We search for the in order in the entire in order array. We search for the pre-order P of 0. Yeah, so we were searching for 3 in this array. We find this index as 1. And we make a node. So we make 3 and we call 3.next. And 3.next we know we have to next guy we have to look at is this guy. Okay, now I am a bit confused here. Yeah, I think this is fine. This is fine. And then in order, and then we know that the maximum that you could get is from L to index minus 1, which is just this. And then we go to 9. We matches this, so it returns. Now for 9, we'll call both this and this. When we call both this and this, uh, this R will become negative. What will happen to P index? Yeah, so P index is fine, but this L and R are the problems, right? So if L is less than 0 or R is less than 0, actually this, why is this 1? This should be index plus 1, right? No, this should be what? P index plus, yeah, this is, something is wrong. So I was looking at P index. Now I look at the next guy, and here I will look at interesting, but I have to fix this again. That I'll do, but one sec. First, let me figure out the base conditions. L less than 0, R less than 0, or L is greater than equal to or dot length, R is equal to okay. And another bit could be, why is this coming over again and again? L is greater than R, right? L should not be greater than R. L should always be less than R. So if any of this condition happens, that means you can't find, you return null. Now let's look at these cases. So for when you were at looked at 0 index, then you want to check index plus 1, which is correct. You want to go to the next guy. and range would be this. So range is correct. Now, when you want to look at the right subtree, in the right subtree, sorry. So when you're trying to create the right subtree, so for 3, when you're trying to create 20, in which index of pre-order array you should look at, right? So you got sorry in order array. So okay, so you know how many children are in the left subtree, and that would be defined by. So okay, let's do this. So L till index minus 1, which is how many? It is index minus L minus 1. Sorry, index minus 1 minus L plus 1. One gets cancelled, so minus L. So these many elements are there in the left subtree. So from and we know that in the pre-order array, first all those elements would be required to be dealt with, and then you go to the right tree. So how many of these would be? So from p index, you if there was one element, then you would move ahead these many elements, and the next guy after this, right? So let's understand. So if index minus L is, let's say, 3, so p index plus 1, p index plus 2, and p index plus 3 would be in the left subtree, and then plus 1. So this is what I want to pass. So it would be index plus index minus L plus 1. Let's try and understand whether this makes sense for our case. So for our case, this is the array, this is the index, which is 1. So p index was 0. So 0 plus index is 1 minus 0, 1 plus 1, 2, which is 0, 1, 2. So from 15 is where you want to check. This makes sense to me. Let's do a dry run for either of those slanting ones. Yeah. So let's do. I want to do the other slanting guy, that slanting guy on the right side. Okay, let's do this only then. This is easy. I want to do the right slanting to verify that. No, I think this is also fine. Let's do this quickly. 1, 2, 3, 4. So, or whichever this guy is. Let's do a dry run for this guy, whichever this is. Did we complete the drive for this though? Okay, let's repeat this. So yeah, we go 3, and yeah, you call pre-order, and basically you go to 9 when you call this, and after 9, anything you do for right or left. Yeah, so we have to see that. Now you come to 9, you search index 9, you find the index, you find 9 here, and now from 9, current 9's dot left would be index. This is fine. These would be problematic because r will become less than 0. Okay, so that's how you will break out from that. 9's right would be, this is doesn't really matter. Basically, you're looking at okay. Let's calculate what we are looking at exactly. P index 0, not 0 here. Okay, so 9 is at index 0. Yeah, but it's P index, right? Yeah. So yeah, our P index is 1. Correct. 1 plus 0 minus 0 plus 1, so 2. Yeah, so you're looking at 15, which is the next element to look at anyways. But in order, this is index plus 1, it was found in order at 0. 0 plus 1 is 1, and r is also 1. Hold on, actually index is for 9, right? Yeah, 9. So to the right of 9. To the right of 9 is 1 till 7. Hmm. So how do you know that nine's right? Yeah, nine's right tree has to be limited by 3, which is the bit that is sort of missing, I feel. No, it's not, because when you called three's left child, right was limited to this. So right is actually 0, and left is also 0. You know, left and right both are 0, and so when you pass this, right would be 0, left would be 1, and this condition of left greater than that would run. Yeah, okay. Okay, this looks good. Run. Okay, where this is, yeah, let's remove this. Run code, and some more spelling mistakes. Right, this works. Let's run example test cases. Come on, mate. Okay, let's try these as well. Okay, first let's try the same guy again. How does it treat this? Okay, this works. And if this lands in the other direction, that works too. Okay, submit. Alright, this looks good. Let's quickly review. Code is pretty straightforward. Let's remove some of these comments, put them elsewhere. Here, this was helpful. Yeah, so basically what we're doing, we're trying to build a tree, we're passing the index in the preorder array, and we're passing the range in the inorder array, the limits, right? And now we handle a bunch of base conditions that shouldn't happen, in which case we return null. We find whatever index we're looking for, that in the preorder, the element in the preorder, we find it in the inorder within this range, LNR, we expect it to find. So we find that, and then we create a new node, and then we recursively do this for left and the right. Now the thing here is, in the left, we just basically know go to the next guy to look at. Now in the right, we can figure out how many elements are there in the left based on this, and based on that, whatever number of elements are there in the left subtree, we have to first traverse that much elements in the preorder array to for the left, and then only we'll move on to the right subtree. We can potentially move to the right subtree. So this would be this, based on this logic, we can figure out the starting index in the preorder array that we have to check for the right subtree, and then these limits gets bounded. All right, all good. So that's that.